As we ponder the mysteries of time, this is the one lecture in which we'll allow ourselves to get a little philosophical. And by that I don't mean we'll just sort of sit back and ponder how awesome it all is and reflect upon the majesty of time and space. What I mean is we're going to think about the problem from a philosophical perspective, from the rigorous academic discipline of philosophy. Now there is, of course, a long-standing relationship between physics and philosophy, or between science and philosophy more generally. There is, let's say, a usually friendly rivalry. The two disciplines are a little bit different. They have absolutely different aims, but their subject matters often overlap. And the study of time is one where the philosophical perspective is absolutely helpful, even to physicists like myself. What philosophers try to do is to really understand the logical inner workings of something. Physicists, like myself, are often very happy just to get a theory that works. A theory that makes sense is a little bit too much to ask sometimes. And you might think this is not possible, but we have it all the time. Quantum mechanics is a great example of a theory that doesn't completely make sense to us, but it works, so for a physicist, that's fine. For a philosopher, they would like to do a little bit better. The same thing is true with time. We have an understanding of how time works in a physical way in certain well-defined circumstances, but there are still philosophical questions. So in this lecture, we're going to sort of lay out what some of those questions are, and that will help us understand the scientific aspects that we'll uncover as we go on through the rest of the lecture. So what do we mean when we say time, especially as opposed to space? What do we mean when we say the whole universe? When we think of the universe, we generally think of space. We think of not just space as outer space, as planets and stars and galaxies, but the space around us, the location of things in the world. The world, the space that defines everything around us and the stuff in the world, that's what we think of as the universe. But we think of that universe as happening over and over again. So we automatically, right from the start, treat time and space differently. We treat space as somehow more important or relevant to what the universe is, whereas time is just a label that tells us which moment of the universe we're talking about. Already in Lecture 1, we discussed this analogy of thinking about the universe as a movie reel or a film strip, a series of frames, a series of moments. And what I'm trying to say here is that both each frame and the whole series of frames, the whole movie reel, define what we think of as the universe. It's this four-dimensional thing, both space and time. And I have to caution, when we use that analogy, it's very tempting to wonder whether or not, like a film strip, moments of time are discrete. As far as we know, nothing in physics tells us that time is discrete. As far as we can tell, time is perfectly smooth and continuous. People sometimes wonder whether or not a future reconciliation between quantum mechanics, the theory that happens at the very small scales, and relativity, Einstein's theory of gravity, maybe someday that will tell us that time really is discrete. After all, quantum mechanics comes from the word quantum, meaning coming in discrete packets. So maybe when you quantize space and time itself, they will become in discrete packets. But as far as we know, that's not true. Their best understanding right now of time and space has time being absolutely smooth and continuous. That's not to say that we will not get a better understanding of it in the future, but right now I'm not trying to use the film strip analogy to say that time comes in discrete packets, just that the universe is both each frame of the movie and the series of all the frames together. So already, the way that film strip of the universe works involves a fairly subtle notion, the continuity of the universe from moment to moment in time. We said before, the universe doesn't rearrange itself, unlike space. So let's sort of interrogate that concept a little bit more closely. In space, what happens at this point right here seems more or less completely disconnected from what's happening at this point right here. Now, it's true that in the real world, things do not completely change from point to point in space. Here is the air in the room, here is the air in the room also. But I could put, my hands very close to the ground, and then you would have air here and the ground right next to it. There's nothing to stop me, in principle, from having absolutely empty space at this point and some incredibly dense or incredibly hot or incredibly interesting object right next to it. Space, the stuff around us and the stuff inside space, doesn't have any rules about what comes next to everything else. Time, on the other hand, has rules about what comes one moment after the other. That's how the laws of physics work. That's how we think of the laws of physics in the modern world. And this is not at all the only possible way the laws of physics could work. This is a really interesting, profound feature of the real-world laws of physics, namely that the way they work is the following. You tell me what the world is doing right now, or at some other moment in time, but you tell me everything in the world at one moment in time, and the laws of physics will tell you what happens next. And then from that next moment, the laws of physics will tell you what happens the moment after that. So the laws of physics start from a moment, start from a state of the universe at one instance in time, and they tell you, using the patterns, using the physics, the equations that are the laws of physics, what happens at each subsequent moment. That's completely different than space, obviously. In space, the laws of physics are not able to tell you, just because something is happening in this place, what will happen in the place next to it. Even when it comes to time, it could have been different. Remember, Aristotle discovered laws of physics that worked in terms of the future. Things have goals, and to understand what will happen next, you need to contemplate what the future conditions could be. We could contemplate different laws of physics that involved the past in some important way. That knowing the universe right now wasn't enough, and you needed to know how it got there. But as a matter of fact, the laws of physics that we use, whether they're from Galileo or Newton or Einstein or Schrödinger or superstring theory that we talk about today, they all have this feature that what happens at one moment of time is enough to predict what will happen at the next moment of time. And after that, you can just keep predicting all the way toward the future. So to really get our brains wrapped around this, think about the difference between time and space. Later on, we'll talk about relativity and how they're related to each other. But let's for right now just accept the ordinary notion that time and space are completely different. We move through space as we like. We can choose to go to some other location in space. We can't choose to go to some other location in time. We inevitably move through time at the rate of 1 second per second. Time is relentless, whereas space is sort of up to us how to move in it. That gives us a certain perspective on what the world is. We think of reality as one moment in time. We think that a location far away, 20 feet away or 20 miles away or 20 million miles away, it might be inaccessible to us right now, but that doesn't mean it's not real. We think of different locations in space as absolutely real, whether or not we are there. But now think about time. Think about the past and the future. Are they real? And this is a question where as soon as you start thinking about it, you begin to suspect that the answer is just, this is not a good question to ask. Nevertheless, it's important to understand why we think of different times differently than different spaces. We think of the universe right now as existing, but we think of the past as over. We don't think of the past as real in the same way that the present is. And we certainly don't think of the future as just as real. So the important thing is not to figure out what is real and what is not real. The important thing is to wonder, why do we treat the past and future so differently? Why are we thinking of them in such a different way as we think of the different parts of space? So to answer that question, we should think about how we use these concepts, how we actually go about describing space and time. Let's imagine you want to meet someone for coffee. You say, let's be at a certain cafe at 6 p.m. What you're really doing is giving them coordinates in the universe, what a physicist would call an event. You need to specify space, where you are going to meet, and also time, when you are going to meet them. Now, fortunately, we live in a world where we're basically stuck to the surface of the Earth, so giving someone a coordinate in space is giving them, an address, or two numbers, let's say, what street you're on and which number you are on that street. But if you were to meet them anywhere in space, you need to give 3 numbers. Space is 3-dimensional. You have length, breadth, and height. Time is another dimension on the universe. We can marry together the 3 dimensions of space to the 1 dimension of time to make something called a 4-dimensional space-time. That space-time is the collection of all the different elements in the universe. Now, you might think that the notion of space-time is something that Einstein gave us. But it's just as important to think that Newton, who preceded Einstein, could have talked about space-time. He had space, he had time. Newton knew as well as Einstein did that to locate someone, to meet them somewhere in the universe, you needed to give 4 numbers, 3 locations in space and 1 number for what time you would meet them. The difference is that to Newton, space and time were just so different that there was no temptation to marry them together. You could have done it. It wouldn't have been against the rules, but there was no benefit to doing it either. Einstein, as we will see, showed that what counts as space versus what counts as time will be different to different people, so you need to think of them as space-time. Once you start thinking about the universe in that way, you hit upon a different possible way of thinking about the world. Our everyday way of thinking about the world, the philosophers would call presentism. Presentism is the idea that what exists, what is real, is the 3-dimensional universe at some moment in time and everything in that universe. The past and the future, those are not real. The present moment is real, the past is memory, the future is prediction. But physics suggests a different point of view. Physics says that if I knew the universe exactly right now, I could predict what the future would be, and I could also reconstruct what the past was. The laws of physics connect the present moment to the future moments and to the past moments. So from that perspective, we begin to think that the past, the present, and the future maybe are all equally real. This is a point of view called eternalism, as opposed to presentism that says the present is real and the past is a memory, the future is a prediction. Eternalism says all of the moments in the history of the universe are equally real. There's nothing special about the present moment except that you are experiencing it right now. You might think that this is a difficult way of thinking about the world, and it is difficult because it's not our usual way of going through life. Sometimes the point of view of eternalism is called the block universe perspective, because you try to imagine stepping outside of the universe and seeing the whole 4-dimensional thing as one block of both space and time. This is sometimes called the view from nowhere, the view from not any one moment in time, but outside the whole shebang. Kurt Vonnegut once wrote a novel called The Sirens of Titan, where he had characters, aliens, called Tralfamadorians. And the Tralfamadorians had a special feature that they lived outside time. They experienced the block universe just as you and I would experience 3-dimensional space. They could choose to, go to the year 1600 or go to the year 2500 after breakfast that day. Now, when you think about it carefully, which I know is not the job of a satirical science fiction novel, but if you were to think about this very carefully, you'd realize the Tralfamadorians don't quite make sense. We can talk about the 4-dimensional universe, but if you imagine an alien species that could decide to go and visit the year 1600, then clearly they have a personal notion of time. They weren't visiting the year 1600 yesterday, they will be visiting it tomorrow. So really, you're just adding a whole new dimension of time to the universe. It's something you can imagine doing, but it's not the universe in which we live. For us, the task is to take ourselves outside our everyday experience and imagining looking at this 4-dimensional block universe, to treat the past, present, and future on an equal footing. This seems to be the right way of looking at things as suggested by the current laws of physics. I should be honest in saying that it's a controversial point of view. Many philosophical stances are controversial. There's certainly philosophers out there who don't believe in eternalism. To me, it seems to be the logical consequence of the physicist's way of looking at the universe, but it should be kept in mind that there are other ways to do it. What does it mean if it is true that the past, present, and future are equally real, we certainly think of them very differently. We treat the future very differently from the past. Another way of thinking about our sort of folk, traditional, everyday way of thinking about the universe is the growing block universe model. So I said that presentism treats the present moment as real, the past and future are not real. So a slight twist on this idea is to treat the present and the past as real, but the future not yet. This fits in very well with our notion that we get to make choices about the future. We don't get to make a choice about what to have done yesterday, but we get to make a choice about what to do tomorrow. So the past is fixed, it's in the books, it's real. We might not be living there, but it happened, it's settled. Whereas the future is up for grabs, so maybe we should treat them very, very differently. This seems natural to us as human beings, but it has no reflection in the ultimate laws of physics. It is not something that we get any warrant for from our best understanding of the universe. The better way to say it, I believe, is to understand that the reason why we treat the past and the future so differently is because of the arrow of time. In other words, it's not time itself that treats the past and present and future differently. It's the arrow of time, which is ultimately, as we will see, dependent on the stuff in the universe, on our macroscopic matter and the configurations that it's in the entropy of the stuff in the universe that started out low and is growing and will continue to grow toward the future. It's the arrow of time that gives us the impression that time passes, that time flows, that we progress through different moments. So from that perspective, we understand that it's not that the past is more real than the future, it's that we know more about the past. Our memories access moments in the past. And when I say memories, I don't just mean the actual memories in our brains. I mean any record, any fossil, anything that we can look at that we believe gives us reliable knowledge about the past. We live in a world where memories exist, where there are history books. There are no history books written about the future. That's the difference between them, which can ultimately be traced to the arrow of time. So it's not that the past and the future don't exist, it's that we have different access to them. We were in the past, and the memories of that past are still reflected in the present day. But that's ultimately because of entropy growing. We'll discuss that in great detail. But it bears on this question of what is real and what is not real. The answer is that all moments of time seem to be real, but some we understand better than others. That's something we're going to be developing when we get to the reflection of the arrow of time and how we think and about how our brain processes information. So all this is a little bit philosophical, as we promised. So let's get more concrete about how it plays out in the everyday world. We mentioned that one way of thinking about time is that time is what clocks measure. We live in a world full of clocks. And an important thing about clocks is that time doesn't simply pass. It's not just that there's earlier and now and later, but that we can measure it. You can say not only has time passed, but a certain amount of time has passed. 1 second is shorter than 1 minute, which is shorter than 1 day. There is an amount of time that we can quantify using clocks. So what a clock is something that does the same thing over and over again in a repeatable way. And then you might ask, isn't this whole thing circular? Isn't it that we're defining time as what clocks measure, and we define clocks as things that do the same thing over and over again as time passes? So I want to take the opportunity to say that it's not a circular definition. There really is some substance to the claim that time is what clocks measure. A clock is something that does the same thing over and over again, but the existence of things that do the same thing over and over again in a predictable way is not taken for granted. We might have lived in a universe where everything that repeated itself did so unpredictably. The important feature of clocks is that there is more than one clock in our universe. We're lucky enough to live in a universe that is full of clocks. I mean, of course, that by clocks, something with which we can measure the passage of time. The earliest clocks were not on our wrists or on our computers, they were in the sky. The Earth rotates around its axis. It also revolves around the Sun. These are two different things that the Earth does, and they do that in a predictable way. They are comparable to each other. Roughly speaking, the Earth rotates 365¼ times every time it revolves around the Sun. And the nice thing about that is that it is predictable. It's not a different number of days for every year. It's the same number year after year after year. That's what makes the motion of the Earth give us reliable clocks. And it's not the only one, of course. We have the moon, we have the other planets, we have the stars in the sky. The sky gives us repetitive phenomena that we can use to measure the passage of time. So you might ask, what are the other good clocks in our universe other than those that we get in the sky? It's certainly not our memories. We experience the passing of time, but we all know that experience is not very reliable. Sometimes we think a lot of time has passed, other times we're not so sure. We think that very little time has passed. What we're looking for in a good clock is something that can be relied on. It does the same thing over and over again. Obviously, the rotation and revolution of the Earth is an obvious choice. Another one is the rocking of a pendulum back and forth. That is why we put pendulums in our grandfather clocks. These days, on our wristwatches, the best clocks will be in the form of quartz crystals. You can actually make a certain quartz crystal in the shape of a tuning fork that is guaranteed to vibrate back and forth exactly 32,768 times per second. The reason why that number is chosen is because it is 2 to the power of 15. So you can take 32,768 and divide it by 2 15 times. You can divide the time periods up as finely as you want to. Quartz is both reliable and predictable. It won't matter what the humidity is, what the temperature is. That quartz crystal will tell you the time to very high accuracy. This search for reliable clocks isn't always an easy one. Let's go back to the idea of the pendulum rocking back and forth. It turns out to be true that the rocking of a pendulum is a pretty good clock, but it's certainly not obvious. You might think that if the pendulum was just moving a little bit, maybe it goes faster than if it's moving a lot. This was actually shown not to be the case all the way back in 1583 by none other than Galileo. He was a young boy, he was going to church, like all young boys in Pisa in Italy did at that period of time. But occasionally he would get bored sitting around in church, and because he was Galileo, he did little mental science experiments. So Galileo noticed there was a chandelier hanging from the ceiling of the cathedral in Pisa, which is still there, you can visit it today. And the chandelier rocked back and forth, and sometimes it was only rocking a little bit, sometimes some air had disturbed it and it was rocking a little bit more. And Galileo got the idea in his head that it seemed that the amount of time it took the chandelier to go back and forth was the same. No matter what the amplitude of the rocking was, the time was approximately the same. The question is, how would he check this idea? He was an empiricist. He wants to do an experiment to figure out whether this idea is on the right track. And again, because he's Galileo, he realized he could compare the rocking of the chandelier to the beating of his heart. Galileo calculated that he could count his pulse while he was watching the chandelier go back and forth, and what he realized is that his conjecture was correct. That no matter what the amount of rocking was, the frequency, the time it took the pendulum to go back and forth, the chandelier hanging from the ceiling, it was going to be the same. This is the basis we have for pendulum clocks even today. It's not the absolute most reliable way of telling time we have, but for the 16th century, it was a very, very good step forward. We still use that way of timekeeping today. You can imagine, like we said, a different world, a world in which there were no regularities, that there were no such good clocks anywhere in the universe. There were things that happened over and over again, but they happened at unpredictable rates compared to each other. This would be a very strange world to live in. It would be completely crazy from our point of view. It's a world in which you couldn't measure the passage of time. There would be no reliable clocks. There would still be time. There could still be the idea that there was a moment before some other moment, but you could never say how much time had passed from one moment to the other. So in a way, we're very fortunate, at least scientists are very fortunate, that we live in a world where time can be measured, a world in which clocks exist and we can build them and they will tell us how much time has passed. The reason why clocks are so important when we think about time is because they give us an operational way of thinking about time. You can easily get yourself mixed up thinking about the fundamental nature of time. And clocks help us because they refer to things that really happen, not just to abstract concepts. So questions like, are the past and the future equally real, may or may not be interesting questions, but you can ask, what would a clock do? That's an interesting question. That gives you an answer one way or another. So consider, for example, a favorite thought experiment. What if time were to simply stop? What if time ceased passing everywhere in the universe? Or, alternatively, but just as well, what if time slowed down everywhere in the universe? What would that mean? Give you time to think about it. The answer is, it would mean absolutely nothing. If time stopped everywhere for everything in the universe, there would be no way of knowing. You would stop, the processes in your brain would stop, your pulse would stop, your breathing would stop, so you would not experience any time at all because time has stopped. But at the same time, all of the clocks would stop. The earth would stop rotating, the pendulum would stop rocking back and forth. So when you compared the amount of time felt by any one object in the universe to the amount of time experienced by any other object in the universe, time stopping everywhere leaves no trace whatsoever. While I am lecturing to you right now, you might imagine that time has stopped and you'd never know. But then you realize that if time has stopped, you can't even say, well, time has stopped for 1 century. That doesn't mean anything because time has stopped. So when you get lost in these questions about the meaning of time, what is real and what is not real, it always is helpful to go back to what do clocks do. There's a story that illustrates this very well. There's a novel written by Nicholson Baker called The Fermata. It's about a man who can stop time. He just has a magical ability. It's not explained. It's not hard science fiction or anything like that. Here's just a person who can decide to stop time whenever he wants to. But obviously he's not stopping time everywhere in the universe. He himself keeps time going. If you read the novel, which is a good read, it's interesting and thought-provoking, the man himself is not an admirable character. He mostly uses his ability to sort of make people look foolish in different ways. He's not saving the world. But we as scientists can ask, or philosophers, what would it mean for someone to be able to stop time? Well, how would that really work? Forgetting about could you do it, forgetting about the technology problem of how you would build a time-stopping machine, what would actually happen if you could stop time for the rest of the universe while you yourself kept going? Well, you would quickly realize that even if you grant the possibility of such a thing, it doesn't actually work like it says it would work in the novel. For one thing, if you stop time for the rest of the world, let's say everything more than 3 feet away from you, time stops. Suddenly you can't see anything more than 3 feet away from you. There's no light coming to you from any of those things that are outside your time-stopping zone because time has stopped. You cannot breathe anymore if the air in the room has stopped moving. If you started to move through the air and these other air molecules are absolutely stationary, they would be a brick wall to you. You could not even walk in such a room. So when you actually sit down to think about what it means to stop time, or even for time to move at different rates for different people, it's actually a very, very slippery notion. We will later see when we talk about relativity that there is a well-defined scientific sense in which different people can measure time moving at different speeds. But the only way they can do that is by being in different places in the universe or moving through the universe at different rates of good old-fashioned velocity. If you're stuck near a black hole, or if you're in a spaceship moving very, very close to the speed of light, then the amount of time that passes on your wristwatch will be different than the amount of time experienced by someone who stayed back at home. But if you're looking at your wristwatch, it will seem to move at the absolute conventional rate, because you and your watch, any clocks you bring along with you, all are traveling together. You all experience the same passage of time. I think that in some ways in the modern world, time has a bad reputation. We feel that we are slaves to the passage of time, that there's a clock, there's a calendar, we have to get things done, there are deadlines, and they get in our way. But if you think about it, all of these aspects of time are social. The reason why time presses on us is because we are trying to coordinate with the outside world. We have a clock, someone else has a clock, we agreed to meet for coffee at the same place at the same time. Time is only pressing us when we want to match our actions in the world with the actions of somebody else. I would argue that is not fundamentally a bad thing. We should not blame time for this. We should be grateful we live in a world that lets us coordinate and be social creatures.